Hello viewers, today we want to look at maximization problems in linear programming using the Simplex method. Maximization problems in linear programming using the Simplex method. Now, to understand this, let's pick a question. In the course of solving the question, all the concepts you need to know to understand the maximization problems in linear programming using the Simplex method will be explained to you. So let's look at a question like this. Maximize z equal to 6x1 plus 8x2 subject to 5x1 plus 10x2 less than or equal to 60 and 4x1 plus 4x2 less than or equal to 40. Then x1 x2 greater than or equal to 0. So let's assume that we have a question like this. Maximize z equal to 6x1 plus 8x2 subject to these constraints. So this is the objective function and these are the constraints. We call the last constraint the non-negativity constraint. Now, when a problem is given to you to maximize, or when any arithmetic problem is given to you to solve, the first thing to do is to write the problem in standard form. So this problem has to be written in standard form. So let's quickly write this problem in standard form. In standard form, this problem, so solution. In standard form, the problem will be, so let me write it this way, in standard form, the LP becomes the problem becomes, so you write it in standard form, maximize z equal to 6x1 plus 8x2 plus, we are going to continue this one. Let's concentrate on the constraints first. Subject to. Now, when you have a less than or equal to constraint, you want to transform this one into an equality constraint. In standard form, all the constraints should be equality constraints. So this is you have a less than or equal to constraint here. So we are going to add what we call a slack variable to the left hand side. And as soon as we do that, it will transform this inequality constraint into equality constraint. So, and because slack begins with the letter S, and the first one is in the first constraint. The first one is the first constraint. We are going to add S1 to the left hand side of this constraint, and it will transform it into equality constraint. So subject to, so the first constraint will be 5x1 plus 10s2 plus s1. That is slack variable 1 in the first constraint, and this is equal to 60. Then similarly, the second one, let me write this file well. We are going to have 4x1 plus 4s2 plus slack variable 2. That is, it means it is in the second constraint. So if it is in the third constraint, s3, these are subscripts. So this is equal to 40, and then we say that x1, s2, s1, s2 greater than or equal to 0, and then go back to your objective function. Because the question are not giving, the question did not contain the slack variables, they will go with 0 coefficients in the objective function. 0 coefficient. So this is the standard form of the problem we were given to solve. And so we have added a slack variable to this one, the first one, and a slack variable to the second one. So a slack variable is therefore a non-negative variable which is added to the left hand side of a less than or equal to constraint to transform it to an equality constraint. Again, a slash variable is a non-negative variable which is added to the left-hand side of a less than or equal to constraint to transform it into an equality constraint. Now, having written the problem in standard form, you go ahead to solve it. Now, if there's a problem with the standard form of the problem, then the solution will not be correct. So you have to always ensure that the standard form of the problem has been well written. Now, having written this, then you have to construct what you call a simplex tableau or a simplex table. So let's look at the table like this, and then when you construct the table, then you try to fill it. Fill it this way. C is a script, a capital B, and this is BB, this is CJ. Now, CB means the coefficient of the basic variables in the objective function CB. The coefficient of the basic variables in the objective function. BV means basic variables, and then CJ is the coefficient of all the variables in the objective function. Now, so let's come back to the problem in standard form. This is the problem in standard form. We are going to look at the constraints here. Now, a basic variable is a variable that appears once in the standard form of the constraint and has coefficient 1. Again, a basic variable is a variable that appears once in the standard form of the constraints and has coefficient 1. So you look at the constraints here and look at the variables that have appeared once and have coefficient 1. Now, if you look at x1 is here, it is also here. So we see this to be a basic variable for now. And then x2 is also here, it's also here. So it can never be a basic variable. Now, s1 has appeared once in the standard form of the constraints, and s2 has also appeared once in the standard form of the constraint. And both of them have coefficient of +1. If this one were to be negative, then S1 would have ceased to be a basic variable, but because it is positive, S1 is a basic variable. So basic variable is the variable that appears once in the standard form of the constraints and has coefficient 1. So now, having identified the basic variables, you go ahead here and then write, these are the basic variables. We have S1 and then S2. And then CB means the coefficient of the basic variables in the objective function. So the coefficient of S1 here in the objective function is 0, as it is clearly indicated here. So this is 0, and the coefficient of S2 in the objective function is also 0. Now, here I'm going to write all the variables. We have S1, S2, S1, S2. So we are going to have S1 here, S2, S1, S2, and this is what we call the right hand side. The right hand side, or at times you can call it solution. And this one you are calling theta ratios. Theta ratios. I'll explain that when you get to that one. So we have it this way. Now you go back here, CJ, the coefficient of all the variables in the objective function. So the coefficient of S1 in the objective function is 6. And the coefficient of S2 in the objective function is 8. And that of S1 is 0, S2 is 0. So you write these here, 6, 8, 0, 0. And then you come down here. This one, you look at the first, these two rows will be filled using the coefficients corresponding to the constraints. So the first constraint, the coefficient of x1 is 5, and then s2 is 10 in that order. So this one is 5, this is 10. The coefficient of x1 in the first constraint is 1. You don't have s2 in the second constraint, so the coefficient will be 0. And the right hand side value is 60. Or what we sometimes call the solution is 60. Now the second one, we have the coefficient of S1 to be 4, S2 to be 4, and then, so this is 4, this is 4. We don't have S1, so the coefficient will be 0, and that of S2 is 1. And then the right hand side is 40. Now, having obtained this, we calculate what you call ZG. So ZG. ZG, for this one, if you want the value to write here, this is what you do. 0 times 5 plus 0 times 4. So 0 times 5 is 0 plus 0 times 4. So this one will give you 0. The next one, 0 times 10 plus 0 times 4. That is also giving us 0. So what it means is that when you see that ears are, the values here are 0s, you don't have to think. All these should be 0. Now what this means is that if you want to stop, if the stopping criterion is met, then this will be the objective function value. So we have to check. Can you stop? You find what we call Cj. Next, we find what we call Cj minus Zg. Now, when all the Cj minus Zj values are less than or equal to 0, then we have every right to stop. It means that the optimal solution has been found. So this is Cj. The Cj values are here, and these are the Zg values. So 6 minus 0 will give us 6 for the first one. 8 minus 0 will give us 8. 0 minus 0 is 0. 0 minus 0 is also 0. And as I have already indicated, when all the Cj minus Zg values are less than or equal to 0, you can stop. So clearly here you can see that we cannot stop because of these two numbers. We cannot stop. Now if we cannot stop, then you see we started with these basic variables S1, S2. Then what this means is that one of these basic variables must leave the basis. And this position will be taken by the maximum Cj minus Zj value. So in this case, it is 8. So you bracket the 8 this way. You just bracket it. And go up here and bracket. Let me use a different marker. And go up here and bracket the numbers here. That's the numbers corresponding to the basic variables. So we have it this way. So I have bracketed. Let me even use blue pen here. I have bracketed the number here because it has the maximum Cj minus Zj value. So it means that now S2, this 8 to S2 is going to be a variable, and one of these basic variables will leave, and this position will be taken by the S2, which was not a basic variable. So at every point you have to update the basic variables. Now, if S2 is going to be a basic variable, then which of these old basic variables you leave? So you want to be fair. You know, in order not to be biased, you go and take what you call theta ratios. It's like taking penalties. So you come here, the theta ratios. You are going to take theta ratios for S1 and then S2. Now this is how you take the theta ratios. For the first one, the S1, you take the right hand side value, which is 60. And then you divide it by the bracketed number for S1 here. That is 10. And this is giving us 6. And then the next one, this one will be 40 divided by the bracketed number, which is 4. And this is 10. So the basic variable with the minimum theta ratio will leave. It's like penalties. You are taking the penalties. This team has scored 10. You have scored 6. So definitely this team has lost. So if S1 has lost, S1 must leave the basis, and this position will be taken by S2. So this is the leaving variable. So X2 is the entering variable, and S1 is the leaving variable. So we can say that an entering variable for maximization problems, an entering variable is a variable with a maximum Cj minus Zj value. That is, or let me put it this way, an entering variable is a non-basic variable with a maximum Cj minus Zj value. And a leaving variable is a basic variable with a minimum theta ratio. Now let's continue. So S1 will leave, and information will be taken by S2. So let's continue the table. So this S1 will leave. So this information will be taken by S2. So S2 has come here, and in fact you don't have to change the positions. S1 was first, so S2 should come and replace it. It should be first. Now you go and look at the coefficient of S2 in the objective function. That is the standard form, and the coefficient of S2 is 8. The coefficient of this S2 is 0 in the objective function, because these are the coefficients of basic variables in the objective function. Now, because X2 has replaced S1, look at where you bracketed. This is the most important number here. So let's copy the numbers. I'm using my blue pen so that when I'm okay with the values here, I can use my black pen. So students, you can use your pencil to write this. When you are okay with the numbers there, then you can use pen. Okay, so I've written these numbers. Now look on the board. Look at the number which was bracketed, 10. The number which was bracketed is 10. Look on the board. Currently, these are the basic variables. Before that, let me show you something, so that when you are getting things from, you see. This is a basic variable. Basic variable versus itself will always give you 1. Look at it. S1 versus S1 has given us 1. S2 versus S2 has given us 1. Now a basic variable versus another basic variable will be 0. So S1 versus S2, 0. S2 versus S1, 0. And at every stage, we get new basic variables. So currently, these are the basic variables, X2 and then S2. Now look at the board. This was the number which was bracketed, the 10. Look at it. X2 versus S2 should give you 1, because a basic variable versus itself should give you 1, and this one is 10. If you were to be 1, then it means that you have to just leave the numbers as they are. But this one, the number here is 10. And you can't leave it like this, because a basic variable versus itself should give you 1. So what this means is that you should find a way to make this one 1. So what you normally do is that we divide through the entire row by something. So you can divide through this one. When you divide this one by 10, you're going to get 1. And when you do that, when you take a decision, you should affect all the numbers in that row. So we are going to divide this one by 10. When you divide this by 10, you are going to get 1. And then you divide this one by 10. That will be 1 over 2. You don't write decimals here. Fractions are allowed here. And then you divide this one by 10, 1 over 10. Divide this one by 10, 0. Divide this one by 10, you are getting 6. And now, these are the numbers. These are the accepted numbers. That's why I've used the black pen. Now, so let's check. A basic variable versus itself is 1. A basic variable, S2, versus S2 is 0, because these are the current basic variables. So look at it. So at every stage, you have to check. If these conditions are satisfied, then it means you are on the right path. Otherwise, you have to correct any mistakes in what you have done. Now, the next one. Because this is 1, look at S2. These were the values of S2. We had 4, 0, 1, 40. These are the old values of S2. Now look on the board. Still, this number was bracketed, and we concentrated on this. We had this to be 1. Because this is 1, any number here, which is in the same column with the 1 here, should be 0. Or, look at it. S2 is a basic variable. A basic variable versus another basic variable should be 0. So it means that this number 4 should be 0. If it is already 0, then you can just repeat all the numbers. You can just leave the numbers as they are. But this is 4. So you should find a way to make this 4 to be 0. So what you normally do is that, since you always use new things to change old things, and these are new numbers, you are going to use this one to make this one go to 0. And when you take a decision, it will affect all the numbers here. So if you have 1 and want to use 1 to take 4 to 0, what you can do is that you can multiply the 1 by 4. You do something to the new to change the old. So 1 times 4, and then you subtract from this 4. So 1 times 4 will be 4. You subtract from this. So 1 and 4, it will give you 0. And this is a decision you have taken. So this 1 time also times 4, and then subtract from this and write the final answer. So this times 4 will be 2. Half times 4 will be 2. You subtract from 4, you are going to get 2. This times 4 will be 4 over 10. And then you subtract from 0. That will be negative 4 over 10. And you always want to write the answers in the simplest form. So 4 over 10. 4 over 10 subtract from 0 will be negative 4 over 10. That is negative 2 over 5. So this is negative 2 over 5. The next one, this times 4. This times 4 is 0. You subtract from this, and you still get 1. This times 4 will be 24. When you subtract from this, you get 16. Now let's check before you continue. Look at it. So x2 versus x2 is 1. The basic variable versus itself is 1. S2 versus another basic variable, this S2 is 0. S2 versus itself, look at it. S2 versus S2 is 1. S2 versus X2 is 0. So it means that we are on the right path. So at this point, you find the ZG again. And as I explained during for the first one, 8 times half plus 0 times 2. 8 times half is 4. 0 times 2 is 0. So we are going to get 4. 8 times 1 is 8. This will give you 0, so 8. This times this plus this times that. So 8 times 1 over 10 will be 8 over 10. And this will be 4 over 5. You always write the answer in the simplest form. 8 times 0 is 0. 0 times 0 is 0. So this one will give us 0. 8 times 6 is 48. 0 times 16 is 0. So that will be 48. Because this times this plus this times that. So you have it this way. Now, can you stop? So you find your Cj minus Zj values. When all the Cj minus Zj values are less than or equal to 0, you have every right to stop. So let's find it. And the Cj values are constant as far as the parent is concerned. They are constant, they are just up there waiting for you. So we have 6 minus the current Zj, this one will be 2. 8 minus 8, this is 0. 0 minus 4 over 5, negative 4 over 5. 0 minus 0 is 0. And then have it this way. Now, can you stop? You cannot stop because of these 2. This is okay, this is less than, this is 0, this is less than 0, this is also 0. But because of the 2, you cannot stop. If you cannot stop, then you bracket these 2. You bracket these 2 and go up here and bracket the numbers here. It means that x1, look at 2 corresponds to x1. It means that x1 will now be a basic variable. If it's going to be a basic variable, then the current basic variables here, one of them must leave the basis. So which of them should leave? So again, you go and take your penalties because you don't want to be biased. You're going to take the penalties here, and the penalties here. For the first one will be 6. The first one will be 6 divided by 1 over 2. And when you are dividing 6 by 1 over 2, it's like multiplying by 2. So this one is 12. For example, 4 divided by 1 over 2 will be 8. Then this one is 16 divided by these 2. The first one was 6 divided by 1 over 2. 16 divided by 2. So this one will be 8. So clearly, This one has the minimum theta ratio. So it means that S2 must leave the basis and its position will be taken by X1. So this one has not been touched, so it has to maintain its position S2 like this. And then this S2 is going to be replaced by X1 because X1 has the maximum CJ minus LJ value and is now the entering variable. So this one will be X1. Have it this way. Now, as we always do in various houses, when you give birth to a newborn baby, at times a newborn baby will say that I want rice, and everybody in the house will take rice. Yes, so we have to first of all attend to the newborn baby. When the newborn baby is satisfied, the rest will also be satisfied. That is why here, when this was the newborn baby, the S2, you attended to it first, and you use the newborn baby to change the rest. Okay, so we have to attend to the new basic variable first, and the new basic variable is X1. So let's look at it. The X1 is replacing S2. So let's write the values here. You have these are the values of S2. So 2, 0, and because X1 is a new basic variable here, which has replaced S2. This S2, you have copied the values of S2 here. Now let's check. That's why I've used the blue pen. When you're okay with the numbers here in the row, then I'll use the black pen. X1 is a basic variable. X1 versus itself should be 1, and this one is 2. So clearly something should be done to this 2 to make it 1. And as we have already done, we have seen similar examples. We can divide through this one by 2 to make it 1. And when you take a decision, you should affect all the numbers in that row. So 2 divided by 2 will be 1. 0 divided by 2 will be 0. Negative 2 over 5 divided by 2 will be negative 1 over 5. 1 divided by 2 will be 1 over 2. 16 divided by 2 will give us 8. So let's check it. X1 versus X1 is 1. X1 versus S2 is 0. Because currently these are the basic variables. S2 and then X1. Now this is 1. So this is the most important number here. Because we bracketed 2 here. So it should be. Now we are going to, so this is 1. If this is 1, it means that any number here must be 0. Now let's look at the values of S2, the original values. You had 1 over 2, 1, 1 over 10, 0, and then 6. And you are saying that X2 versus X1 should be 0, because a basic variable versus another basic variable should give you 0. So we are going to use this newborn baby, this new basic variable, to change this one to 0. So how do you use 1 to change 1 over 2 to 0, to convert 1 over 2 to 0? So what you can do is that you can multiply 1 by 1 over 2, that is half, and subtract from this. You do something to the newborn baby to change those who are already in the system. So 1 times half, then subtract from this. Now this one will give us, so this one will give us 0. Because 1 half and then this one, so that will give us 0. This one times half will be 0. You subtract from this, you still get the 1. This times half, let's look at it here. Let me even clean the question. Can clean the question here. Can clean this, I can work. This one times half will be negative 1 over 5 times half. This is negative 1 over 10. Are you seeing it? And we are subtracting from 1 over 10. So it will be 1 over 10 minus 1 over 10. You have to be very, very careful when you are doing some of these things. Because this one times half, and we are subtracting from this. So 1 over 10 minus minus. So this will be 1 over 10 plus, minus minus will be plus 1 over 10. This is 2 over 10. And this is 1 over 5. So this one will give us 1 over 5. So 1 over 5. Let me do this. The next one. This times half will be 1 over 4. And then we are subtracting from 0. That is negative 1 over 4. This times half will be 4. We are subtracting from 6. This one will be 2. We have addition. And then here, don't forget to write the coefficient. The coefficient of x being the objective function is 8. You can even look at this one. And the coefficient of x1 in the objective function is 6. Now you are going to find our zg. We are going to find our zg. So the zg, as usual, 8 times 0 plus 6 times 1. So this will be 6. 8 times 1 plus 6 times 0. This is 8. 8 times 1 over 5 plus 6 times negative 1 over 5. So this one will be 8 over 5 minus 6 over 5. This is 2 over 5. Are you seeing it? So 8 over 5 minus 6 over 5. That is 2 over 5. You have to ensure that all the numbers here are correct. Then the next one, 8 times negative 1 over 4 will be negative 2 plus 6 times 1 over 2, which will be 3. So negative 2 plus 3, that is 1. The next one, 8 times 2 is 16. And then 6 times 8 is 48. So 16 plus 48 will be 64. Now, can we stop? Let's again find our CG minus ZG. And as I've already indicated, for maximization problems, you can stop when all the CG minus ZG values are less than or equal to 0. So let's check. And the CG values are either 6 minus 6. This one is 0. 8 minus 8. This is 0. 0 minus 2 over 5. Negative 2 over 5. 0 minus 1. Negative 1. So now you can see that all the Cj minus Zj values are less than or equal to 0. So you have every license to stop because the optimal solution has been found. The optimal solution is the best solution as far as the problem is concerned. You can't have a solution which is better than the optimal solution. So you stop and then and say that. So this is how to conclude. You can say that since all the Cj minus Zj values are less than, or let me just put it this way, or since all the Cj and Zj values are less than or equal to 0, we stop. We stop. The optimal solution is therefore Z equal to, now look on the board. You come here, the Zj, this is the final Zj value, 64. So this is the objective function value, the optimal objective function value, 64. This is 64. And you say, and it occurs at x1. So you go to the table, look at the final iteration. This is the final iteration. x1, the right hand side value or the solution is 8. x2, the right hand side value is 2. So x1 is 8. It occurs at x1 is equal to 8. x2, which is equal to 2. x1 cannot be found in the last iteration. You can't find it here, x1. So if you cannot find it there, it means that this value is 0. And then x2 is also equal to 0 because it cannot be found here. So this is the optimal solution. This is the optimal solution for the problem. Now let's check whether what you have done is right. You see that the objective function was to maximize z equal to 6x1 plus 8x2. So let's do the substitution and then see. And then when you do the standard form, or let's just look at this one. When you put 8 here, you're going to have 6 times 8, which will be 48. So 6 times 8 plus 8 times 2 is equal to 48 plus 16, and this is 64. And you see that we had the z to be 64. So clearly, what we have obtained is the optimal solution. So this is how maximization problems in linear program using the Simplex method is done. Now for more of this video, subscribe to my YouTube channel so that anytime I put something there, you can have access to it and then download. Thank you very much for your attention.